You ever look at a galvanic cell problem on an exam and just freeze? Yeah, they can look pretty intimidating, but trust me, they're just a puzzle. And today, in this explainer, we are going to take one apart, piece by piece, so you can totally master them for good.
So here's our plan of attack. First, we're going to figure out the basics of the cell. What are the parts? How much juice does it have? Then, we'll actually put it to work and see how it physically changes things. After that, we get to play detective and solve for a mystery solution. And finally, we'll wrap it all up with the big takeaways.
Okay, first up, the challenge. Let's get the lay of the land. Understand exactly what we're dealing with. Every little detail here is a clue.
All right, so what do we have here? On one side, you've got a solid gold electrode sitting in a solution of gold ions. Simple enough? But on the other side, things are a little different. We've got a platinum electrode, which is inert, by the way, with chlorine gas bubbling all over it. Now, these two halves are connected by a salt bridge, right? That lets the ions flow and completes the circuit. And of course, there's a voltmeter hooked up, just waiting to tell us which way those electrons really want to go.
Now, this is the key to the whole puzzle. These E0 values, the standard reduction potentials, think of them as a measure of electron greediness. It's that simple. The higher the number, the more that half reaction really wants to grab electrons. And it's this difference in greediness that's going to power our entire cell. It's the whole reason it works.
Okay, so now that we have those potential values, we can get to the real heart of it, figuring out which electrode does what. And once we know that, we can calculate the cell's total voltage. Its fundamental power.
So the big question is, how do we decide which way the electrons are going to flow? Well, the most important thing to remember here is what actually drives the whole spontaneous reaction in a galvanic cell. And it all comes down to that difference in reduction potential between the two halves.
And the rule is actually super simple. The more electron-greedy side gets to be the cathode. That's where reduction happens. So in our case, gold is sitting at plus 1.50 volts, and that easily beats chlorine's plus 1.36. So, bam, the gold half cell is our cathode. That means by default, the chlorine reaction has to be the anode. And this is key. It's going to run in reverse as an oxidation. So even though the table shows chlorine gaining electrons, in our cell, chloride ions are going to be losing them.
All right, we've got our roles assigned. Gold is the cathode where all the reduction action is. The platinum electrode is the anode. That's our site for oxidation. Now for the fun part, the math. We just take the cathode's potential and subtract the anode's. That gives us a positive 0.14 volts. And that positive sign, that's absolutely crucial. It's like the universe giving us a thumbs up, telling us, yep, this reaction is going to happen all by itself.
But wait, we're not done yet. To write the full reaction, we have to make sure the electrons balance out. What's lost must be gained. So gold needs 3 electrons, but oxidizing 2 chloride ions only gives us 2. So what's the smallest number they both go into? 6, right. So we multiply the gold reaction by 2, the chlorine reaction by 3, and voila, we have our final, perfectly balanced equation for everything that's going on in this.
Okay, great. So we know the cell can produce a voltage, but what happens if we actually hook it up and let it run for a bit? Let's say we draw a current, half an amp for 30 seconds. Is anything physically going to change in there? Well, let's find out.
So, if we want to find out how the mass of an electrode changes, there's a clear 4-step plan. First, we use the current and time to figure out the total charge that's passed through. Then, we use our magic translator, Faraday's constant, to turn that charge into the actual number of moles of electrons that have moved. After that, it's all just good old stoichiometry. So let's just picture what's physically happening at that gold cathode. You've got these gold ions, the Au3+, just swimming around in the solution. They come up to the electrode, they grab some electrons, and poof, they turn into solid metallic gold plating right onto the surface. So yeah, the mass of that gold electrode is definitely going to go.
And when we actually crunch the numbers, we calculate the charge, convert it to moles of electrons, use our mole ratio, what do we get? We find that the gold electrode gains exactly 0.01 grams. I know, it's a tiny amount, but it's real. It's a measurable, physical consequence of those electrons getting to work.
Okay, but what about the other side, the platinum electrode? Well, the platinum itself isn't actually part of the reaction. It's just a stage, an electrically conductive surface where the chloride ions can do their thing and oxidize into chlorine gas. That's why we call it an inert electrode. And because of that, its mass doesn't change one bit, stays exactly the same.
All right, let's switch gears completely. Let's tackle a new challenge, one that is super common in a real lab. What if? What if you don't actually know the concentration of one of your solutions? Could you use the voltage of the cell to figure it out?
To do this, we need a special tool, the Nernst equation. This thing is so powerful because it connects the dots between concentration and voltage. See, a higher concentration of reactants gives the reaction a bigger push, and that directly affects the voltage you can measure. The Nernst equation lets us quantify that.
So check this out. A student swaps out the standard 1 molar gold solution for our unknown. And look at the voltmeter. It's now reading 0.12 volts. Now remember our standard potential, it was 0.14 volts. Since this new voltage is lower, that's our first big clue. It means the reaction has less of a push, which tells us the reactant concentration must be lower for sure. It is not 1 molar.
And this is where we let the Nernst equation do its magic. We just plug in everything we know. The new voltage, 0.12, the standard potential we already found, 0.14, the number of electrons zipping back and forth. The only thing left is Q, which has our unknown concentration hidden inside. We do a little bit of algebra and mystery solved. The concentration is 0.097 molar.
But wait, is that the only way to solve this? Not at all. A second student comes along with a totally different idea. They propose building a whole new type of cell to find that same concentration. Let's see how this clever approach works.
Honestly, this student's idea is brilliant. They suggest building what's called a concentration cell. You use two identical half cells, so gold electrodes in gold solutions on both sides, but, and here's the trick, with different concentrations. The cell generates a voltage simply because nature wants to equalize those two concentrations. It's so clever.
And here's the standard shorthand for that new cell. A really easy way to remember this notation is anode on the left, cathode on the right. A, C, just like the alphabet. That double line in the middle, that's our salt bridge. In a concentration cell, the lower concentration side is always the anode, because that's where oxidation happens to try and bring that concentration up. So, what kind of voltage would this new setup even produce? Well, we go back to our friend, the Nernst equation. Now, a really cool thing about concentration cells is that their standard potential, E0, is always 0. Why? Because the electrodes are identical. So we just plug in our two concentrations, and the math tells us we should expect a voltage of 0.02 volts. It's a totally different way of doing it, but it's a fantastic way to double-check our work.
Okay, so after breaking down that entire problem, let's zoom out for a second and recap the big ideas we used. These are basically the essential tools for your chemistry toolkit. And here they are, what I like to call the 4 pillars of solving these problems. 1. Higher potential wins. That's your cathode. 2. E cell equals cathode minus anode. That's how you get your standard voltage. 3. If you see current and time, think Faraday's law. And 4. For anything weird with concentrations, the Nernst equation is your best friend. Honestly, you master these 4 concepts and you can handle just about any galvanic cell problem they throw at you.
And you know, this stuff isn't just for an exam. The exact principles we just walked through, they're happening right now inside every single battery you use. Your car, your phone, you name it. It just goes to show you, electrochemistry is literally all around us, powering our world. Makes you wonder, what else is it doing that we don't even think about? Thanks for joining.